Thank you everyone for coming, and thank the organizers for this great workshop. So I will explain to you our joint work with Theo and Yao on Ramanujan property at edge universality of random regular graphs. So this talk, I will have this three parts. First, I will have a quick background on random graphs and random matrices. In particular, some statistics about Tracy-Widom distribution. And second part, I will discuss our main results on the eigenvalue rigidity at the edge universality. And last part will be some proof ideas. We use the loop equations and some local resampling to prove the edge universality. And if you have any question during the talk, feel free to interrupt me. So one key concept in graph theory are those expander graphs. So they are very sparse graphs, which means they are not many edges, and they have a very strong collectivity property, which means if you remove some edges, the graph is still collected. And like these two properties make the expander graphs pretty useful, and they are used to, since they are born, they are used to build robust computer networks, error correcting codes. And mathematically, for the strong collectivity property, it's measured by this following Cheeger's constant. So it's minimum over all the vertex sets, the number of edges between S and the complement over the smaller part. So if a graph has a bottleneck like this one, then the Cheeger's constant can be small. And if the Cheeger's constant is bigger than 0.01, then to make the graph into this collected two component, you need to remove many edges proportional to the smaller part. And the main topic of today's talk are random d-regular graphs. So it turns out for expander graphs at early time, actually it's not that hard, easy to construct. But if it turns out if you just sample a random d-regular graph, they will give you a very good expander graphs. So the model we study is just a uniform probability measure on the set of simple d-regular graphs on n vertices. Just among all those d-regular graphs, you randomly pick one. Now here is an example of a three-regular graph. And for given the d-regular graph, we denote A, the adjacency matrix. Yeah.
It's easy to construct such graphs.
There are several ways to construct it. One is you can use the configuration model. You have n vertices, each has d half edges, then you do a perfect matching. And some other ways is not exactly this one, but you can also take some of d copies of random random perfect matching matrices, or you take d over 2 copies of random permutation. Or you just start from any d-regular graph, run some Markov process. You will get, that's an approximation. But if you want to get a precise one, you just do the configuration model. Just n vertices and each has d half edges. Okay, so for us, like for the adjacency matrix, each vertex has a degree d, so it has a trivial eigenvector 1, with eigenvalue d. And if we further normalize the adjacency matrix by dividing by square root d minus 1, then the total variance for each row is now of order 1. And for normalized adjacency matrix, the largest eigenvalue now becomes d over square root d minus 1. It turns out this normalization, all the other eigenvalues are roughly between -2 and 2. And if you just look at the empirical eigenvalue distribution of those random d-regular graph, then it converges to the Kesten-McKay distribution depending on the degree d. So the first part. And the second part is just a perfect semicircle from -2 to 2. So here is a simulation for random 4-regular graph. The eigenvalue histogram is this blue part, and the red curve is the Kesten-McKay for d equals 4. So you see they match pretty well. So even in a very small bin, the number of eigenvalues is well predicted by the red curve. This is called the eigenvalue rigidity. I will explain later. And here, this is an outlier, largest eigenvalue. This Kesten-McKay distribution was discovered by Kesten when he studied the spectral measure of d-regular tree at McKenzie for random d-regular graphs. And I mentioned we are discussing about the expanding property, so it's given by this Cheeger's constant. But it turns out the Cheeger's constant is, in the worst case scenario, it's NP hard to compute. But there is another concept of expander graph called the spectral expander. So because the Tigers constant can be approximated roughly the same order as the spectral gap, the gap between the largest and second largest eigenvalue. This is a result by Tanner, Allen, and Millman. So for any irregular graph on n vertices, there are some universal constants, only depends on the degree d, does not depend on the size of the graph. The Tigers constant is the same order, like a lower and upper bounded by the spectral gap, lambda 1 minus lambda 2. So spectral expander graphs are defined as a sequence of irregular graphs. The size goes to infinite, and the spectral gap is lower bounded by, say, some delta. And you can see this random sampled four-regular graph. There's a pretty large gap between the largest eigenvalue, so it's a good expander graphs. It turns out the random sampled irregular graph, they will give you very good expander graphs. So looking for good expander graph, natural question is, what are those irregular graphs has largest possible spectral gap? Because lambda 1 in our normalization is constant d over square root d minus 1. So largest spectral gap means the smallest possible second largest eigenvalue. And this question was answered also 30 years ago by Allen and Bopana. Like for any irregular graph collected, second largest eigenvalue is lower bounded by 2 over some constant times over the diameter of the graph. If you have a sequence of irregular graph, if the size goes to infinite, the diameter of the graph will be at least of log n. So asymptotically, the smallest possible lambda 2 will be just a 2 over. This quantity goes to 0. So leaving for the smallest, second largest eigenvalue is at least a 2. So asymptotically, the largest possible spectral gap is just lambda 1 minus 2. And because of that, in the famous paper by Lubatsky, Philip, and Salak, they coined the term Ramanujan graph. So a irregular graph is called the Ramanujan graph if all those non-trivial eigenvalues, you ignore the largest one. And if the graph is bipartite, it has the largest eigenvalue d and smallest eigenvalue minus d. So for that case, you also ignore the smallest eigenvalue. So all those non-trivial eigenvalues are strictly less or equal than 2. Then they are called the Ramanujan graphs. So asymptotically, they have the largest possible spectral gap. So they are best possible expanders. So the most important results for those Ramanujan graphs is they do exist. And this was proven in the same paper by Lubatsky, Philip, and Salak, and also independently by Margulis. They prove using some number theory technique. If P is a prime, then there exists a Ramanujan graph with degree D is a prime plus 1. To show those graphs, they constructed a Ramanujan graph. They use the Ramanujan conjecture proven by Delin. That's why they are called the Ramanujan graphs. And since then, one major open problem in this field is, does there exist a Ramanujan graph or infinite family of Ramanujan graph for any degree D? This question was answered more than 10 years ago by Marcus Spielman and Shrivastava. They proved there do exist infinite family of bipartite irregular Ramanujan graphs using the method of interlacing polynomials. Their original proof is linear existence proof. Later, some polynomial algorithm was proposed by Michael Cohn. But this is only for the bipartite Ramanujan graphs. It's still an open problem. After this, does there exist an infinite family of non-bipartite Ramanujan graphs for any degree D? So if you have any Ramanujan graph, if you look at a double cover, bipartite double cover of it, you will automatically get a bipartite irregular Ramanujan graphs. But because we are all mathematical physics, and it turns out if you just do some simulation, like at a very early time, like 40 years ago, like they don't have like a computing power to really simulate random irregular graph, check they are Ramanujan or not. And if you really do a simulation, now it's pretty easy. Just ask ChatGPT to do it. You can just realize at least one thing is like it turns out easy to see a portion portion, like a positive portion of those de-Rieger graphs are Ramanujan graphs. And if you just refine the simulation, it was observed, it turns out for those random de-Rieger graph, second largest eigenvalue and smallest eigenvalue are all well modeled by Tracy-Widom beta equals 1 distribution from the GOE. So here is just some quick slides on the random matrix and some statistics I will use later. Let's just look at the GOE matrix. Normalize each entry has a variance 1 over n. And you plot the eigenvalue distribution, you get this perfect semicircle from -2 to 2. If you just take out the largest eigenvalue, concentrate around 2, subtract 2, rescale it by n to the 2/3, you get Tracy-Widom beta equals 1. If you do the same thing for GOE, you get Tracy-Widom beta equals 2. And for those Tracy-Widom distribution, it's biased towards the negative axis. 83% of the mass is on the negative side. So for GOE matrix, 83% of the chance, the largest eigenvalue is less or equal than 2. And it was also proven to be universal, the so-called edge universality. So essentially, you take any real symmetric random matrices. As long as those entries have 4 moments, slightly weaker than that, then you will always have those Tracy-Widom distribution as the scaling limits of the largest and the smallest eigenvalue. And motivated by those universality results, purely based on the numerical simulation, Sanlak and Miner-Lovakoff-Sibali, they make this conjecture for G, which is a random de-Rieger graph on n vertices. Take out the second largest eigenvalue, do the same scaling as the GOE matrix, but you need to further normalize it by some constant dependent on D, and shift it by another, possibly shift by another constant. You will get the Tracy-Widom beta equals 1. And they also conjecture the same is true for the smallest eigenvalue. So you do need to do this further normalization. So here is some simulation I did. You just sample a lot of 3 regular graphs, plot the histogram for the second largest eigenvalue, subtract 2, and rescale by n to the 2/3. It gives you this blue part. And this red part is, you can think is Tracy-Widom from the GOE. If you don't further normalize, they look different. But if you further center them and normalize to be variance 1, they actually look pretty similar to each other. And another, like this last simulation was I borrowed it from the paper by Miner-Lovakoff-Sibali. And in the original simulation, you can see this to the 2/3, this exponent is for sure, but it's very hard to see what are those constants, normalization constants. Like this simulation is, if you just look at to those random theoretical graphs, sample a lot of them, figure out what is percentage of them have a second largest eigenvalue less or equal than 2. So like these different curves correspond to slightly different theoretical graph models. Like you can look at configuration model, or you can look at those sum of permutation matrices. So at the beginning, it turns out if you use clear horizontal axis is the size of the graph. Like it goes from 0, 5,000 to up to 20,000. Vertical axis is a percentage which has lambda 2 less or equal than 2. At least at first for those very small graphs, it turns out like if you do simulation, more than 90% of them are Ramanujan graph. But if you increase the size of the graph, like this probability is slightly goes down. And this 83% is from, if there is no shift, if it's really come from the GOE, we should expect this percentage should be 83%. You can see it seems it's slowly converged to 83%, but at that time, like if you only go to 20,000 vertices, it's hard to guess if this will eventually goes to 0 or not. And our result essentially proves this conjecture, and this shift C2D is 0. Yeah. So let me just, so for our result, like for those random de-Rieger graph, like if the edge universality is true, then, which means the second largest eigenvalue should concentrate around 2 on a very small window of size n to the -2/3. So even to show they concentrate around 2 is not a very easy task. And it was first a conjecture by Logan Allen about 30 years ago. He just conjectured for random de Rigueur graph. They are nearly Ramanujan graph, which means lambda 2 concentrates around 2. And this was proven in the famous paper by Friedman, and later a new proof was discovered by Bodinov. They prove for random de Rigueur graph, like it's true for all those models, like I mentioned, the second largest eigenvalue concentrates around 2. And in their original proof, it's based on moment method. So this concentration is not that good. It's given by log n over log n square. So again, like the correct one, if the edge universality is true, this should be n to the minus 2/3. And later in the joint work with Yao, we managed to show like this concentrate with some polynomial error, but this C cannot be too large. We can only get its 0.01, but it's some polynomial concentration bound. And last year in the work by Chen, Gaza, Vargas, Tramp, and Van Handel, they come up a very general approach to prove the strong convergence for random matrix models. Essentially, if you have a very complicated random matrix model, they can show the largest eigenvalue concentrate around some number predicted by free convolution. As specialized to those random de Rigueur graph, the result gives a concentration. This little one can be some log n over n to the 1/6. And the first result of our work is the concentration of eigenvalues. It's not just for the largest eigenvalue. We can do it for all the eigenvalues together. So if you look at the 3 Rigueur graph, we can introduce this classical eigenvalue location gamma I. So which is you take out the Kesten-McKay distribution, this red curve, and look at the 1/n quantiles of it. So those integrate from gamma I to 2 is given by I over n. So it's 1/n quantiles of the Kesten-McKay distribution. So we can prove with a probability close to 1 minus n to the minus c, I's eigenvalue concentrates around gamma I. A concentration, the bound is given by n to the minus 2/3 plus little 1, which is some small number, can be arbitrarily small, times the minimum of I times n minus I plus 1 to the minus 1/3. So for this I, if you look at those extreme eigenvalue like second one, third one, or smallest one, nth eigenvalue. So this part is just some constant, you can ignore it. So this is the extreme eigenvalue concentrates with error n to the minus 2/3. And if you look at the eigenvalues inside the bulk, like I is like of n over 2, for example, then this second factor is of order n. So the whole thing is roughly 1/n. So this is the best one can hope because there are n eigenvalues on the interval from -2 to 2. So the typical gap is of order 1/n. So this is about the concentration for all the eigenvalues. And the next result is the edge universality. We essentially prove this conjecture. And this C2D, this number, it's 0. There's no shift. And this C1D, this number is precisely given by this number depends on d times d minus 1 over d minus 2 square. And the reason you have this rescaling by this constant is if you look at the Kesten-McKay distribution, it also has a square root behavior at the edge. And if you just Taylor expand it, the density behaves like A times the square root of 2 minus x. If you look at the semicircle distribution, Taylor expand, you will not have this constant A, it's just a square root of 2 minus x. So rescale by this A just to make the curvature the same. So that's the reason you have this normalization. And then you don't need to do any further shift of it. You will get a Tracy-Widom beta equals 1. So this is for the fixed degree D. And for the larger, if you allow D to grow with the size of a graph, then the graph is, the adjacency matrix is not that sparse. It's not look more like those very dense GOE matrices. It turns out easier, and that was known before in the joint work with Roland, T, and Yao, and also another work with Yao. We managed to prove as long as D grow like n to the epsilon, and much smaller than n to the 1/3, you have convergence to the Tracy-Widom. And in that case, if D grow with the size of a graph, this normalization constant is just goes to 1. So you have almost essentially the same statement as the GOE. You don't need to do further normalization. If the graph is very dense, D is much bigger than n to the 2/3. Yuquan also did it to prove the convergence of Tracy-Widom. And we believe if he further push his arguments should also cover the gap between n to the 1/3 and n to the 2/3. So essentially for any D, we should have the Tracy-Widom distribution. This is really a very robust phenomenon. And back to those Ramanujan graph, if essentially for this one, we can prove something slightly stronger. We can show the second largest eigenvalue converge to the Tracy-Widom, and also the smallest eigenvalue after the same scaling, it converges to the Tracy-Widom distribution. And the two just converge to independent copies of the Tracy-Widom distribution. So from the statistics of the Tracy-Widom distribution, 83% of the chance you have lambda 2 is less or equal than 2, and 83% chance you have lambda n is bigger or equal than -2. So just multiply 83% with 83%. You get 69% of those de-Rieger graphs are Ramanujan graphs. So in fact, you have a lot of those Ramanujan graphs. Okay, so next I will explain to you the main proof ideas. So far, any question? Now maybe a good time for questions if you have any questions. Yeah.
So the rigidity estimate is on the same event all of the eigenvalues posted for possible.
Yes, so essentially for the rigidity event is you need to condition on certain type, this comes from your condition on the graph to be each neighborhood contains at most one triangle. So that basically is true with 1 minus n to some minus 0.01, depending on how big the neighborhood you want to take. And if you condition that type of graphs, then actually you can show with very high, with high probability 1 minus n to some minus arbitrary large number. If you do the conditioning, this rigidity is true. Other questions? Okay, so next I'll explain to you the main ideas of the proof. One idea is the microscopic version of those loop equations. So the interesting fact for this problem is original expander is a concept from computer science, and their construction use number theory tools. And finally, our proof use mathematical physics tools from loop equations. And other ideas are local resampling. So for those loop equations, there are many origins for those loop equations. One origin is from those 2D quantum gravity. There is this beautiful result if you compute the trees for the case moments for the Gaussian unitary ensemble divided by n. So you have 1/n expansion. And for this 1/n expansion, this coefficient SGK, they count the number of different ways to glue these K guns such that you get some surface of genus G. So obviously that K has to be an even number. And you can also not just look at the trace of h to the k, you can also look at those moments of the GUE and take the product of their trees. And you also have those 1/n expansion, first obtained in the physics community and proven also in the math community. And for us, instead of the trees of the moments, we will use the Stieltjes transform. You can essentially think it's another way to encode all those moment information. Just Stieltjes transform of the eigenvalues is given by 1/n trace of h minus z inverse. So you just take z large, Taylor expand, it encodes all the information of the trace of h to the k. So essentially, if you have the Stieltjes transform for the 1/n expansion, then you will automatically get 1/n expansions for the trace of moments. And specialize for those matrix ensembles like GOE or GUE. You can integrate their eigenvalues or eigenvectors to get those Gaussian beta ensemble. And so beta is 1 is for GOE, beta equals 2 for GOE. So there are a lot of study for those Gaussian beta ensembles. They have many fascinating properties, like this normalization constants can be computed by Silberg integral. And although this only beta is 1 to 4, you have GOE, GOE, and GSE. But for any beta, you also have a tridiagonal model obtained by Dumitru and Edelman. And if you write down those loop equations for those Gaussian beta ensemble, essentially you will get some recursive structure satisfied by those Stieltjes transform. So if I denote the Stieltjes transform is Sn, and you have a bunch of those equations. So although they may look a little bit complicated, but it's actually not easy, not that hard to derive them, essentially just obtained by integration by parts. So the first equation is this one, like the first part is this quadratic equation of the Stieltjes transform, s squared plus ds plus 1. And this second part, you have some 1 over n correction given by the derivative of the Stieltjes transform, and some number depends on beta. And then you can also have just if you just look at the multiplication of the Stieltjes transform, you see if you think Stieltjes transform as a correlation function, you can view them as some recursive structure of those correlation functions, like p-point correlation functions. You will get this equation, the same blue part as the first equation, and then you multiply p minus 1 copies of the Stieltjes transform at different locations, z1, z2, up to zp minus 1. And all those these are on the complex plane, like they are not on R. And this is the first part, involve p copies of the Stieltjes transform. And the second part, it's some 1 over n squared correction. So it's given by this part is snz minus snzj over z minus zj, and derivative with respect to zj. And then you multiply some snzi, I is not j. So this part you can think it's involves the multiplication of p minus like p minus 1 copies of the Stieltjes transform. So essentially, you can view it as some recursive structure, like p-point correlation functions is related to p minus 1 point correlation functions. So those are the loop equations for the Gaussian beta ensemble. So they can be analyzed and get 1 over n expansions for the expectation for the Stieltjes transform. Thus, you can recover the result I showed you those 1 over n expansion for the trace of the moments. And more generally, you can look at those beta ensemble with some potential V. If V is quadratic, you go back to the Gaussian beta ensemble. And those loop equations, you can also write them down for those general beta ensembles. They are introduced to the math community by Yang Hansen to study the eigenvalue fluctuations of those beta ensembles. And later, they also play a very important role in proving the eigenvalue rigidity and universalities for those beta ensembles in the work by Paul, Laszlo, Yao, and Bakerman, Figali, Alice, and Shubina. And the thing is, for those beta ensembles, if you write down the loop equations, they will depend on the potential V. So they are not unique. You will have model-dependent loop equations. But the key observation we have is if you zoom in around the edge, the spectral edge, it turns out you will get something universal. So it will not depend on the potential V. So like if you look at the Gaussian beta ensemble, lambda 1, lambda 2, you have n eigenvalues. So if you just scale the largest eigenvalue, it converges to the Tracy-Widom beta distribution. As you can imagine, you can do the same thing for all those extreme eigenvalues, lambda 1, lambda 2, lambda 3, all together, subtract 2, and rescale it by n to the 2/3. The whole thing will converge to the area beta point process. So for beta is 1 and 2, this was first proven by Tracy and Widom. For general beta, this was proven by Ramirez, Ryder, and Virank using those tridiagonal models. And so for this area beta point process, you can do the same thing, just write down the Stieltjes transform. So we can just denote those particles lambda 1, lambda 2, lambda 3. So it's an infinite particle system. It's one side extends to the infinite. So you just denote YW is summation of 1 over lambda I minus W. And roughly you can think because of the square root behavior, lambda I behave like minus if you lambda 1 is roughly at 0. Those particles, if you go inside the box, it gets denser and denser. So those lambda I is behave like 1 over minus I to the 2/3. So this summation does not converge. So you need to further normalize it, so just subtract something. Then this is still a well-defined quantity. And again, because of the square root behavior, this YW, if W goes to infinite, it has the square root behavior because you have the square root density. So you can essentially think for those airy beta point process, the Stieltjes transform is a random meromorphic function. It defined on the complex plane, and the poles are given by those point locations lambda 1, lambda 2, and lambda 3. So it encodes all the information of those airy beta point process. And then you can also formally at least take the limit of the loop equation I showed you in last slides. You will get those loop equations. The first one is again something quadratic. So it's YW minus square root W square, and you have this square root W times their difference and derivative of Y. And you can also have those P point loop equation of rad P, the same as this red part, and also the product of P minus copies of Y. Here is the product of P minus 1 copies of Y. So formally, you can always just write down the loop equations for any matrix model you want. You just, if you don't care about if you can take limit or not, formally take the limit. It turns out you should also always get this set of equations universal. And sort of you should, the edge universality, if you view it this way, it comes, can be think it comes from this set of equation is unique. And another way to think about universality is this has a square root behavior. If you Taylor expand around the roots, there's really not much choice. You have to get some quadratic equation, and the quadratic equation somehow shift it and rescale it. It's almost only choice. It has to be like this one. So now if we want to show something converges to the airy beta point process, if this statement is true, it's necessary the Stieltjes transform after normalization needs to satisfy the set of loop equation. So this is like back to the Dirichlet graph. Essentially, what we prove is they satisfy those microscopic loop equations. So we denote the adjacent symmetric normalizer 1 by h as a Green's function by gz, which is h minus z inverse. Z is on the complex plane. And the Stieltjes transform is 1 over n times sum of 1 over lambda I minus z. It can also be obtained by the Green's function 1 over n trace of the Green's function, just sum over those diagonal entries. So if you compute, if you believe this eigenvalue distribution converges to the Kesten-McKay, then this Stieltjes transform Mn, it also should converges to the Stieltjes transform of the Kesten-McKay distribution. So you can explicitly write it down, compute it. It has a square root behavior at the edge. If you just Taylor expand around the edge, the Kesten-McKay distribution, its Stieltjes transform is given by this expression. Here A pops up as A times the square root of z minus 2. As a result, we prove is if you look at the Stieltjes transform of the Dirichlet graph, Mn minus the Stieltjes transform of the Kesten-McKay distribution, denote this as delta z. Then for any z1 up to zp minus 1, they are complex numbers. So they satisfy those microscopic loop equations. You first have something quadratic in delta, and multiply p minus 1 copies of those delta. And then here you have this 1 over n squared correction. And here is multiplications of p minus 1 copies of those delta. And you need to prove this with very small error. Error need to be much smaller than n to the minus p plus 1 over 3. If this is true, then you can take the scaling limit because the eigenvalues live on the scale n to the minus 2/3. That's the fluctuation. So we need to zoom in around the edge location 2 and take 2 plus some w over n to the 2/3. and rescale the Stieltjes transform by further n to the 1/3. If you do this scaling, then it converges to the Stieltjes transform of those array beta point process. It converges to this YW minus square root W. And this square root W essentially comes from this MD, and this Y comes from this Stieltjes transform of the eigenvalue distribution. And here, because we multiply the Stieltjes transform by n to the 1/3, so you need this error to be much smaller. Essentially, both sides you multiply n to the p plus 1/3. So this error, just to make sure, you after this scaling limit, this error goes to 0. So you get the loop equations for the array point process. But at this point, it's not clear to us if those loop equations uniquely characterize those array beta process. It will be a very interesting question to explore. But to derive those array statistics, we need to do something slightly more. So we need to show like if this H is the normalized adjacency matrix, we need to further add some Z, which is a GOE matrix times square root T. We need to add some small GOE matrix. And what we need to show is for this deformed adjacency matrix with a small GOE component, if you can prove for this matrix, for any choice of T, all of them satisfy this microscopic loop equation. Essentially, that will tell you, like if you add this GOE, like the local statistics does not change along this time T. And it's also known before in the work by Ben and Yao. Like if for any matrix, as long as you have some estimate for the eigenvalues, if you just inject a little bit noise, add a very small GOE component, you will see those Tracy-Widom distribution. So essentially, if you combine this matrix structure and prove the loop equations for any matrix plus a small GOE matrix, if you can check this loop equations, then you can conclude the edge universality. The extreme eigenvalues, they converges to the array point process. So this is once we have those, you have the loop equations, you need to do something furthermore for those H plus the small GOE, then you can conclude the universality. Okay, so like next remaining 15 minutes, I explain to you how we prove those loop equations for the random de-Rieger graph. So here I will just start with a simple case for the GOE matrix. So essentially, I'll just prove the first loop equation. It's something quadratic in W or in delta, and plus some 1/n correction. So for the first one, you need to show the error is much smaller than n to the minus 2/3. And if you want to show it for the Gaussian orthogonal ensemble, it's actually not that hard. So for the Gaussian orthogonal ensemble, the eigenvalue distribution is close to the semicircle distribution. The Stieltjes transform of semicircle satisfies exactly the same quadratic equation, m semicircle square plus z m semicircle plus 1 is 0. And in many previous works in random matrix theory, the way we prove the rigidity is to show the Stieltjes transform of the eigenvalue distribution, like it's close to the Stieltjes transform of the semicircle distribution. So instead of directly show the two are close to each other, instead one shows they satisfy the same equation. If you compute the expectation for the Stieltjes transform, the same equation, m squared plus zm plus 1, and you can get this error is bounded by the imaginary part of itself over n times the imaginary part of z. And roughly you can think this is 1/n, pretty small. And similarly, you can compute higher moments to show like mn is really satisfy this equation with high probability combined with Markov inequality. And then use the stability, you will get mn is close to m semicircle. And it turns out if you make the computation more carefully do the computation, this error term it's actually precise. You can get essentially by some integration by parts, you will get this equation, this red curve before it's bound as an error. But if you write it down, it's essentially this is the first loop equation. If you just look at the difference of 2 and 1, and here both are quadratic, just you rewrite it as some quadratics in m minus m semicircle, you will get this last equation. And now if you take this z to be close to the edge location 2, this will be like 2 times the square root of z minus 2. So essentially you will get the same thing as this one, and A is 1 for the GOE matrix. So you can roughly think the loop equation is first get some self-consistent equation for the Stieltjes transform, and you somehow manage to identify the first correction term, then you will get the loop equations. And really, this type of thing is given by some integration by parts for the beta ensemble or Gaussian matrices. Okay, then back to the random deregular graph. Next, I'll explain to you how we derive those loop equations. What is some self-consistent equation at the correction term? And so for the deregular graph, the key property of them is like if you just look at a large neighborhoods of it, say radius r is of log n. If you look at a large neighborhood of it, most of those neighborhoods are tree. They do not contain any cycles. And even for those which contain cycles, you can just restrict them to the case it at most contain 1 or 2 cycles. So basically locally it's a tree-like. You can restrict everything by just contains at most 1 cycle. Like I'll first give you a heuristic how we get some equation for the Stieltjes transform. So formally for the Green's function, like the Stieltjes transform is given by the trace of the Green's function. So for the Green's function, you just formally Taylor expand it. You get this 1 over z expansion if z is large. So essentially, if you look at ij's entry of it, it's just some weighted sum of the paths from vertex I to j. If you look at adjacency matrix to any power, ij's entry just like pass from I to j of the length k. But you just put some weird weights, like 1 over z to that power. Now, if we look at the Stieltjes transform, it's a trace of the Green's function over n. So it's we need to understand what happens to the diagonal entries of the G. So this GOO, you can compute it by view as this picture. It's just weighted sum of paths from some vertex O back to itself. So for all those weighted paths, if I look at some neighborhood of this vertex O, so it will leave this neighborhood at some vertex J and maybe come back from another vertex. But if this happens, which means it will form some cycle. So if you believe like for large neighborhood, it does not contain cycle, or those terms from the cycle is contribution is negligible, the only main term should only be those walks leave from J and then come back to J and go back the same path and go back to the vertex O. So this is the main contribution of the weighted sum. And for this this part, you can first do, instead of just sum over all the paths, you can first sum over the path which is outside this neighborhood T. So those paths is essentially those paths from J to J and never enter this neighborhood T. For some of those paths, you can, again, it's given by the Green's function, as the Green's function of the entry J with the neighborhood T removed. And for this Green's function, you can further approximate it by the Green's function of the vertex J with only the vertex I removed. Because you think a path, if it's from J to itself, if it does not meet this vertex I, then it's not likely it will enter this neighborhood at all. So this you can further approximate it by the Green's function of J with just its parent vertex I removed. So in this way, we get some approximation of the Green's function GOO. Essentially, you take out this neighborhood and just ignore the remaining of the graph. But you just attach some Green's function on the boundary vertices, just the Green's function of those boundary vertices with its parents removed, GJJI. And the quantity we will use to derive the equation is just average of those boundary weights, just average over all the edges ij, like the Green's function at the vertex j with the vertex I removed. And you come to all the directed edges, there are n times d of them, so you normalize it by 1 over n times d. So next we can do the same thing to compute those Green's function with the vertex I removed gjji. So you can essentially do the same thing, take out the neighborhood and attach some boundary weight q. So this will give us some heuristically some equations for the quantity q. So if I denote for this picture, you take out this neighborhood, because most of the neighborhood is a tree, so we just assume this neighborhood is a truncated d-regular tree, or the vertex has a degree d. Then you remove this vertex I, so now essentially the root vertex has degree d minus 1, or the other vertex has a degree d. So you just truncated truncated d minus 1 array tree. And on the boundary, you put some weight q. Then we compute the Green's function as a weight. We denote this function as fq. And then we will get this following approximately. If you believe this heuristic, q will be approximated given by this fq. So although this involves, if the neighborhood is large, it will involve some very deep tree, maybe of order of depth log n, but it's just a tree. Like a computational tree is although it's not trivial, but it's not that hard. It's very explicit. You can compute this function f. It turns out for this equation, q is fq. It has one fixed point, like one solution. Q is given by Stieltjes transform of the semicircle distribution. And now if you take a q to be the Stieltjes transform of the semicircle, go back to this picture, like compute the Green's function at O with the boundary attached copies of the semicircle distribution, the Stieltjes transform, you will get the Kesten-McKay distribution. So this is basically, at least this should be the correct equation. You actually get the Kesten-McKay distribution for those diagonal entries. But as I mentioned, like this one, even this first step, just do a Taylor expansion, it's not rigorous. In particular, we want to take this z to approach to the edge location 2. And this is only true when z is very large. And if you're close to the spectra, you cannot do this Taylor expansion. And the way we derive those equations is to through some randomness of the graph, because so far everything is deterministic. I haven't told you how to use the randomness. The randomness of the graph is used like in this very simple way. So like there is this simple switching process. You just take out for a d-regular graph, you randomly pick two edges, v1, v2, and v3, v4. You remove them and replace them by those two red ones, v1, v4, and v2, v3. So this simple switching, you randomly pick two edges and switch them. It preserves the uniform distribution. In fact, you can use it to build a Markov process to sample those random d-regular graphs. And this simple switching procedure was first used by Roland and T and Yao to study those random d-regular graph. D is much bigger than log n to the c. And the way we use those simple switching is we want to compute the Green's function at some root vertex. Then what, like it will be affected by a large neighborhood of it. So we use it is we just take any vertex and take out a large neighborhood of it, like maybe some log n neighborhood of it. Then we just, for each of those boundary edges, so like for example, this one, each of those boundary edges, we uniform randomly pick another edges in the remaining of the graph. For this one, pick this one. For each of those pair of those edges, we do a simple switching. So if you look at the picture, essentially what we did is just take out the neighborhood T and replant it at some randomly picked locations. And for those randomly picked locations, typically they are far away from each other in the graph distance, and they will have large tree neighborhood. Then after this local resampling, you can think like the Green's function at this root vertex is quickly mixed. And the Green's function of the root vertex should be roughly very similar to like for each of those boundary boundary point, you just attach a copy of M-sim circle. At the different boundary vertices, they should not affect each other. And so because this simple local resampling, they are built from the simple switching. And so they also preserve this underlying uniform measure. If you just resample it, you still the same law. And more than that is it's actually an involution. So for those simple switching, if you do it twice, you go back to the original graph. So if you G is this first graph, G tilde is this new graph after the local resampling. And the two have they form an exchangeable pair. G tilde has the same law as G tilde G. So once you have some exchangeable pair, like we prove the Stein's lemma, like essentially you can do integration by part to derive equations. That's how we get those loop equations. And to make that proof, like the self-consistent equation rigorous, so like what you can do is to use this so-called Schur complement formula. So it's from linear algebra. It tells you if you have a 2x2 block matrix, how can you compute the inverse? And if you just look at this picture, like we just view this adjacency matrix as a 2x2 block matrix, this A corresponds to this block, just this neighborhood, and D corresponds to the remaining of the graph, and B corresponds to those new red edges which collect the neighborhood with what's outside the neighborhood. And this is the switched graph H tilde minus Z. Now we want to compute the Green's function and see this is the 1-1 symmetry. And the Schur complement formula gives you this formula like which computes this first block. It's given by this first block, the H A minus Z. This is the normalized adjacency matrix for the neighborhood. I subtract B times the Green's function of the remaining of the graph D minus Z inverse times B star as the whole thing inverse. So this may look a little bit complicated at first, but if you really think this A minus Z is an adjacency matrix of this neighborhood, this is just a B, is those red edges. It just B is this red edge goes to something, the remaining of the graph, the Green's function, and B star, you just go back. So effect of this guy is really just attach some boundary weight on the boundary vertices. So essentially, like the self-consistent equation can be justified using this expression. And next, you can use the G and G tilde, they form exchangeable pair, and then you can do integration by parts. That's how we get the self-consistent equation Q minus FQ, and then you also get some correction term, depends on derivative of Mn over N. And this is much smaller than n to the minus 2/3. So if you look at this expression, it's not that complicated. But it turns out in our paper, we took more than 50 pages to verify this. And because like the key is you really want to show this error is really small. And if you just do one simple switching, if this neighborhood is some small number times log n, you will get something, you will get the self-consistent equation, but like this Q minus FQ, the expectation is small, but it's not that small. It's like 1 over n to the epsilon. It's not as small as n to the minus 2/3. And what you need to do is for all the error terms, it may involve error term at different new locations. So for those new locations, then you do another local resampling, just take out a neighborhood of it, do a local resampling, do an integration by part. Then you will get improve the error by 1 over n to the epsilon. And you need to repeat this this type of iteration for arbitrary many steps until you reach the error is n to the minus 2/3. And you can also do the same thing if you look at more copies of this Q minus FQ multiplied together. So all of them will give you the loop equation. And for this one, if you also do the same thing for the Stieltjes transform, you will also have a similar equation. Take the difference and play with it. You can rewrite everything in terms of the Stieltjes transform of empirical eigenvalue, subtract the Stieltjes transform of the Kesten-McKay. It's always something quadratic. So you just tune the parameter, you will get the first loop equation. And the same way you will get those higher order loop equations. You just make sure the errors are small enough. So those are the ideas we prove for those loop equations. Okay, so let me just quickly summarize. So in this work, we prove like for those random Dirichlet graph, about 69% of them are Ramanujan graphs. So there are two key new ideas. One is those microscopic version of the loop equations. So we hope this is a very general like phenomenon for those edge universality or bulk universality. Try to get some correlation, like a recursive relation for the correlation. If the universality is true, it has to be given by those microscopic version of loop equations. And the second new idea is to use those local reshuffling to prove those loop equations. For this second idea, it should be model dependent. So different models you use, there are maybe different ways to take advantage of the randomness, how to do the integration by parts. And once you have those two, you have the universality. So there are also some very interesting questions just pop up. One is it true if you have the loop equations, then you automatically have the area point process? Does the loop equation uniquely characterize those area point process? If this is true, it will give a more direct proof, at least for our setting. And also people study other matrix, random matrix models, like for the polynomial of random matrices, or if you have for those Dirichlet graph, you can think it's a random lift of some base graph. If you have two vertices at the edges among them, and you do a random unlift, you will get a random Dirichlet graph. You can ask the same question if you have any base graph. You do unlift to get a random graph. There is also a notion of Ramanujan graph. And like if one can prove the loop equations for those matrix models, maybe one can prove the edge universality for those more complicated matrix models. Okay, thank you.